Okay, so we have two announcements this morning. The first one is that there are a bunch of deadlines in the summary of the La Semana, or the announcements for this week, okay? So if you are not sure about the deadlines, please check the La Semana and make sure that you're aware of the deadlines, okay? That is the first announcement. The second announcement is I just wanted to check in with folks about tutoring to see how that was going. So I don't really know who's been attending tutoring and who hasn't, but for folks who have been attending, how's it been going? Helpful, not helpful? Okay, so it's been really helpful. That's a couple positive feedbacks. Anyone have any questions about tutoring or things that they wish were a little bit different about it? Like the structure of it? No questions? Well then, with those two pieces out of the way then, let's go ahead and get started. So today we are slated to finish chapter 6, okay? So we're gonna finish chapter 6 today with 6.2, sorry. We're gonna finish with 6.2 and we are gonna begin chapter 7. Okay, so chapter 7 is not on the exam this Friday, okay? So chapter 7, all the stuff we learned, the second half of class today, as well as what we learn on Wednesday, is not on the exam this week, all right? But it will be on exam 3, okay? So knowing that after 6.2 today, you can have a mental cutoff and be like, all right, this stuff is not on the exam, and focus on 6.1, 6.2, and 6.3 for Friday's exam, okay? Oh, one last thing I did want to say is I know that I completely forgot to change the web assign in terms of showing the work. So I think what I'm going to do for the math and writing assignment number 4, I'll just have a place for you to upload a file. And that way, if you choose to do web assign, you can just upload all your work as one file instead of having to like awkwardly type in the math box or, you know, attach separate files for everything. So hopefully that'll make all the homeworks a little bit easier. And my apologies for not taking care of that last week when I said I would, okay? So I'm gonna fix the web assign stuff so it'll be a single file in terms of showing your work. Again, this is a chance for you to kind of practice making sure that you've got like the right kind of work that you need for an exam, okay? So make sure that you take advantage of that. All of this is a chance for you to get feedback around, you know, how you're doing, what's going well, where you need to work a little bit more, okay? So think about it more as like a chance to get feedback and less about like getting a specific grade. All right, so that being said, let's go ahead and start with 6.2. There we go. Okay. All right. So let's go ahead and get started with 6.2. Okay, so 6.2 is the last section that will be covered on exam 2. And so we're going to start here with a little bit of the what we know and what's new. And so things that we hopefully know, we know our unit circle, we know the angles, we know the coordinates, okay? We know our parent functions, the graphs of sine and cosine that we learned on Wednesday of last week. And we even learned how to apply what we knew about graph transformations to these new parent functions, okay? So that is all the things that we hopefully know and feel comfortable with by this time. And what's new is now we're going to take a look at the other trig function graphs. Okay, so we're going to take a look very briefly at like the graph of secant and cosecant and cotangent, but we're really going to focus most of today on tangent and graph transformations that go with tangent. Okay. So as you're kind of preparing for exam 3, the biggest piece of information you should study from 6.2 are these graph transformations with tangent. Okay, the graphs of the other functions I want to show you. I want you to know like sort of like where they come from, but I'm not really interested as much in terms of the graph transformations of those, just because we don't see them as much. There's already so much to know. I really want us to focus on things that will be useful for us in the future. Okay. All right. So if you go to Desmos or any sort of graphing app and you go ahead and graph tangent, you're going to get a picture that looks something like this, okay? And what we're going to see is that we're going to get not waves like we normally have in sine and cosine, but we sort of have these branches that are repeated. Okay, and so we're going to use the picture to talk a little bit about the different pieces about tangent. So one of the things that is different about tangent from sine and cosine is the domain is actually not all real numbers. Okay, so the domain here is not all real numbers. All right, and the reason why it's not is because we have these vertical asymptotes that occur regularly throughout our graph. So for example, over here at pi over 2, okay, there's actually a vertical asymptote. And if we go at 3 pi over 2, there is another vertical asymptote. And if we go to negative pi over 2, there is another vertical asymptote. And if we go to negative 3 pi over 2, there is yet another vertical asymptote. Okay, so these vertical asymptotes actually repeat throughout the entire function. And so the way we write this is we say our domain is all real numbers except x cannot equal. Okay, so we're going to say what x cannot equal, but the all real numbers is a sort of a math way of saying it's everything except for these small things, okay, except for some of these things. And since it's a pattern, we don't have to write out every single one. We can describe the pattern of where these vertical asymptotes are. And so our range, or our domain is all real numbers except x cannot be pi over 2, right? That's that first green line that we drew. That's at pi over 2. But it turns out that it's if you add some multiple, that's the k, some multiple of pi, you're going to get all the other asymptotes. Okay? So k here, k is an integer. Integer just means a whole number like 1 or 2 or 3 or 4 or -1 or -2, -3, -4. So k is some integer. And it's basically saying we add pi a bunch of times. Pi gets added multiple times. Okay? So I'm really more concerned about us understanding how to read that notation than necessarily write it ourselves, okay? But the pi over 2, that's the first vertical asymptote. And then every pi, we repeat that asymptote again, okay? So if we think about pi over 2, if we add pi, well, let's see how we add our fractions. That's the same as pi over 2 plus 2 pi over 2, and that's 3 pi over 2, right? And that's how we get this vertical asymptote. Okay, and if I kept adding pi or I kept subtracting pi, I would get to a different vertical asymptote, all right? So that's the domain of tangent. Now the range of tangent, well, let's trace one of these curves and see if there are any y values that are missing. And so let's do the middle one. So if I trace the middle one, it comes up from the bottom, and it goes over, and then it keeps going up. So what do we think the range of tangents is? Are there any y values that are missing? Yeah, there's no y values that are missing. So the range of tangent is actually all real numbers, okay? And this is because no y values are missing. Now, Ethan, back to your question about how would we write the domain in interval notation, we typically don't, because that would mean we would have to write an infinite number of them, and that's just a lot of writing. So instead, we shorthand it by saying it's all of these things except for these ones that are missing, okay? Okay. All right. Now, also taking a look at maybe just this red curve that I traced in the middle and what we know about even and odd and neither, what do we think tangent is? Is it symmetric about the y-axis? Is it symmetric about the origin? What do we think about tangent? All right, Thea says odd. I would agree that it's definitely not even, right? It's not like cosine or the x squared where it's sort of even on both sides. It's a reflection on both sides. And yeah, we already know from our other papers that this function is indeed an odd function, okay? So tangent is odd because it is reflected, nope, it is symmetric about the origin. Another way we could say that is that f of negative x equals negative f of x. All right. Now, finally, let's talk about the period. So the period really means how often does tangent repeat itself, okay? So this wave, I know this wave in quotations that we drew in the middle part, how long is that along the x-axis? Yeah, it's not 2 pi, but it's actually, it's like a half a pi in the negative direction and then a half a pi in the positive direction. So our period here is actually going to be pi, okay? In other words, it takes pi to repeat each branch of tangent. So it takes pi to repeat each branch of tangent. Now, before we move on, what was the period for sine? Mm-hmm. Exactly, Thea. The period of sine was 2 pi, and the period of cosine was also 2 pi, meaning for sine and cosine, we had to go all the way around the unit circle before things repeated again. But with tangent, we really only need to go halfway around the unit circle before things start to repeat, okay? And that should kind of make sense because since we're dividing the coordinates, if we have two positives and we divide them, that's a positive. But if we have two negatives and we divide them, that's also a positive, right? So as soon as we get to quadrant 3, we actually start repeating again the whole period of tangent, okay? All right, and last piece here about tangent is just thinking that we could use our graph transformations exactly the same way that we did with sine and cosine and even any of the parent functions that we learned in Math 116, okay? And so we want to do a quick summary of this one again. And we could say that we're going to start with our C. So our C is going to do what we call a phase shift. Okay. Or we could say that a plus C means, or x plus C means we go to the left, and x minus C means we go to the right. All right, that's still going to be true for tangent. This is our first transformation. Our second transformation, we sort of work our way back out, is our B value. I'm still looking for us to factor, folks. It will be on the test, I promise, okay? But you have to do this on your homeworks, on your quizzes. You have to get into that idea that like if there's a B value, you have to look to factor it, okay? That was definitely a disappointing part on quiz 6 that I noticed from a bunch of folks is there were folks who just forgot to factor that. And it was in like pretty much every other problem. So you lost a lot of points if you didn't get it, okay? But I would rather take those points away now so that you get the message, so I don't do that on Friday when I grade your tests. I'm like, all right, everything is correct. Everyone learned that lesson, okay? So please, 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 for you and also for me, remember to factor that B value. All right, so this B talks about your horizontal stretch or compression, okay? And the B tells you how many branches occur in pi, okay? So if it's a 2, that means that there are 2 branches in that space. If it's a half, that means that there's a half a branch in that space, okay? All right, what comes next when we're looking at graph transformations in order? Is it the A or is it the D? It is the A, all right? And that was something that some folks missed in terms of the order. All right, so we want to make sure that we stretch our graph vertically as we need before we move things, okay? So A is our vertical stretch or compression, right? And that is something where it's probably easier to see with sine and cosine because we're looking at just stretching that graph, okay? It's a little harder to see the stretch for tangent. We probably won't do it as much for tangent, okay? But it should be something that you're thinking when you sort of practice some of those graph transformations of sine and cosine that you know how to do that vertical stretch, okay? All right, last but not least, we have our D value. And our D value, that one gives our vertical shift, okay? So if I have a plus D, I'm moving up, and if I have a minus D, I'm moving down, all right? So all of this should seem familiar. For us, we are going to be focusing on, let me highlight this so it's clear for us. In our class, we're gonna be focusing on how B and C impact the graphs of tangent. So when you study for the exam on Friday, I wouldn't really worry about studying the vertical stuff with tangent. So I wouldn't really study like how do I vertically stretch tangent, or how do I vertically shift tangent, okay? It's nice to know what it does, but it's just harder to see on a graph because there's no sort of like top of the wave, bottom of the wave that you can sort of stretch out and or compress in, okay? So we're gonna focus on how the phase shift and how that horizontal stretch and compression and how we're gonna remember to factor out that B, that's what we're gonna focus on, okay? All right, before we move on, let me just pause for a moment. Are there any questions so far about the graph of tangent or the graph transformations of tangent? Okay. All good, excellent, excellent. All right, so here's what we're gonna do. We're gonna pop out into some breakout rooms. This is very, very similar to what you did on Wednesday of last week, okay? So in your groups, you're gonna use Desmos to kind of help you draw, predict, and see what happened, okay? A few things to point out before I send you off into your breakout rooms, that on your x-axis, I'm gonna ask you to set your bounds to negative pi and pi. So we're not going all the way to 2 pi because I don't need you to draw that many things. That's really all it is, okay? And we also wanna make sure we are in radians so that we can see things appropriately, okay? The last thing I want to say before we go into our breakout rooms is on the graph, Desmos does not give you the vertical asymptotes, but I would like you to either dot them in, you could draw them in with a dotted line or a dashed line, or if you have a highlighter, go ahead and highlight where those vertical asymptotes are. Does that make sense? Okay, so the vertical asymptotes are not going to be showing on Desmos, but I want you to draw them on your graph, okay? All right, so you're gonna take a look at how B changes the graph of tangent. You're gonna answer some questions. You're gonna take a look at how C changes the graph of tangent. You're gonna answer some questions. And then I'd love for you to start to try the 2 examples that we have here, okay? So we're gonna go into our breakout rooms. If you guys finish the first 2 parts early, then go ahead as a group and start working on what happens when we are including B and C together for the graph of tangent, okay? You can kind of think about like how you can type things into Desmos like 1 step at a time to help you out here for sure. But again, right, I'm looking for you to factor here. Like 100% I want you to know how to factor, okay? So that's the last time I'll say that today, but please don't forget. Okay. All right, so let's go into our breakout rooms for about 15 minutes, all right? We'll kind of see how that goes. And again, sort of work as far as you can, but at the very least, let's get through how B changes graph of tangent and how C changes the graph of tangent, all right? So let me stop sharing this. I'm going to, thank you. Okay, so the center point I would say is that point right there.
Okay, so like 0, 0.
Exactly, 0, 0. And so when we're thinking about moving things side to side, I would move the asymptotes and I would move that center point. Those are probably the easiest features to move.
Okay, thank you.
You're welcome. All right.
I had a quick question too. I still can't figure out why minus C moves stuff to the right where positive things are, and vice versa.
Okay. So if we were to look at just this part, x minus pi over 4, what number can I plug in for x to make the pink part equal 0?
Pi over 4.
Pi over 4. So what that means is we're taking our center point and moving it to pi over 4.
Oh, okay.
Right? And if we kind of think the same way about the x plus pi over 2, what do you have to plug in here to make that purple part 0? You're going to plug in negative pi over 2. And that is your new center point.
Okay, makes a lot more sense now.
Okay. Okay. All right. Any other questions about B and C before we do the 2 examples that we have here? Okay. Well, if you think of others as they come along, please ask. But in the meantime, let's take a look at these 2 examples that we have here for tangent. Okay. And so let's say that we're taking a look at example number 1. The first thing that I want to see everyone write is what happens when you factor out that 2. Okay. So when we factor out the 2, we know that there's an x there because 2 times x is going to give us 2x. And yeah, we need a minus pi over 2, because when we take 2 and we multiply it by pi over 2, we're going to get pi, which is what we had originally. Okay, so please, please, please make sure to get this part done. And then when we start with our equations, what we're trying to do is write down not the whole equation, which is what I saw some folks doing. We're not writing the whole equation here. We're writing which part of it tells us what we're doing for that given transformation. So when we're looking at the parent function, we want to write f of x equals tangent x. And we're going to draw a picture that is that picture, just tangent. And so when I think about the key features, I go ahead and I draw in my vertical asymptotes first. So at negative pi over 2 and at pi over 2, I draw in the asymptote. I draw in the center point that Christina asked about, which is at the origin, 0, 0. And then I sketch the rest of it. I don't really worry about nice points. I just kind of draw something like this. Okay. Now, if you wanted to be fancier, you could say, hey, I know there's going to be sort of like the right half of a tangent curve over there and the left half over there. And it keeps going forever and ever. But again, I don't want us to spend time drawing like a billion of these waves. I just want us to draw enough to kind of get the picture. Okay. Now, the first transformation to happen is we're shifting to the right pi over 2. Okay, and we know that because we think if I have x minus pi over 2, what number do I plug in to make it 0? And it's pi over 2. Okay, so the equation I want us to see that goes with that, you can write f of x or you can write y, but it's just going to be tangent of x minus pi over 2. We don't have the 2 in there because we didn't get to it yet in our transformation, okay? And so this pi over 2, if I'm moving everything pi over 2, where does this left asymptote move to? It's at negative pi over 2. Where does it move to? Yeah, exactly. It moves to 0. So, let me do this. Okay, so the lime green one is going to move to here. Okay, where is like the sea foam green one going to move to? Yeah, that one's going to move to pi. Okay, now the center point, which we want to keep track of, this middle point right here. Okay, where does that one move to? Pi over 2. Good. All right, so once I sort of moved everything, then I can sketch the branch or the wave. Okay. Does that process make sense to folks? Like how we move the different pieces? Okay. Now, because I moved it, there's actually another asymptote, right? That sort of comes in. I could fill in a branch here. Because we sort of slid everything over, now there's room for a new one, okay? And if we were to keep track of the points, like this point right here is this point right there, okay? All right, now that we've got our horizontal shift, now let's talk about that too, the B value, okay? So we're gonna have two branches where there was one. That's one way to think about it, okay? Another way that might make more sense to you is we are compressing horizontally, okay? And the coolest thing about what that means for tangent is it means that our asymptotes actually squeeze in, okay? But they squeeze around the midpoint, the center point. So it's so important that we keep track of that center point. In fact, as soon as I get to this part, I'm gonna draw that center point right there. So I know that point doesn't move. But the asymptotes move around that point. Okay, and that was one of the common mistakes I saw in grading quiz 6 is a lot of folks didn't understand that whatever that center point is, that stays, and then things move around it. So we can't just pick a random point and say, oh, let's squeeze around this point, let's squeeze around that point, let's stretch around this point. It has to be that center point. Okay, so that's maybe even a little bit more reason why we should keep track of that center point so we can see where we move things to. Okay. So this lime green asymptote, the one that's at 0, okay, I have to move that in half as close. And right now, I can see that the number of boxes from the center point to the lime green asymptote is 4. So if I want to squeeze it in so that the distance is half as great, well, I'm going to need to squeeze that in 2 boxes. And I'm going to take the one on the other side, the seafoam one, and I'm going to move that one in 2 boxes as well. And what that's going to give me is a compressed branch for tangent. Okay? So when I compare this picture to the one above, I can tell that I squeezed it in so that it's half as wide now. Okay? Which means that I could fit more of them here.
So if it was like a horizontal compression of 3, would we just count 3 boxes in, or would we like divide it by 3?
The second one.
Okay.
Yeah.
So we would divide so we would divide, like, if it was the parent graph and it was just the compression of 3, we would divide like negative pi over 2 by 3. Okay.
Exactly. I will say this because I'm asking us to draw a lot of things by hand. You'll notice that most of the time I'm going to ask you to double things, or I'm going to ask you to cut them in half. I think it's a little bit harder to draw things with thirds and sixths and stuff like that. So I'm going to try and keep them with nice numbers. So like a half or doubling, okay? But I love that extension of the concept. All right. If I think about how wide one branch is here, okay, I can almost kind of see that it's 4 boxes wide. That means that if I want to draw more of these branches, I have to draw a vertical asymptote every 4 boxes. So I could have another one like here. And that would be another branch of tangent. Okay. I could have another one here. And I could draw another branch of tangent. Okay. But once you get that first one, you can really just kind of repeat the pattern around it. Okay. So let me sort of shrink this all so it's on one page for us. And give you a moment to see if there are any questions before we move on. Any questions so far? All right. Well, if there are no other questions right now, let's go ahead and go through example number 2, okay? All right, so let's say you get a question like this on Friday's exam. The first thing you write down before you do anything else better be this, right? That right there. And if we think about what we need to multiply, well, 1/2 times x will give me the 1/2 x. Plus, you got it, pi over 4, because half of pi over 4 is pi over 8, okay? And so if you think about sort of practicing writing your own problems, you'll notice that most of the ones I've given are like quote unquote nice numbers, like things that are halves or fourths. I'm not throwing in like thirds or sixths or anything like that. So we're really just trying to focus on the nicer numbers here, okay? And I wouldn't expect anything different on the exam. So there's really not that many different variations I can come up with, okay? All right, so when we go ahead and write in our equations, again, we can write y equals or f of x equals, but we start with the parent function. So we don't write all of the equation, we just write the part that we're gonna graph. And we know that we have our center point right here. We know that we have one vertical asymptote here. We know we have another vertical asymptote here. And then we have the branch that kind of goes in between, okay? So if you draw like the ugliest branch on the inside, I don't really care, honestly. But what I care about is you've got the right center point, that you've got the right asymptote, all right? Yes, we have technology to take care of the rest. So what I'm looking for is like, show me that you understand the transformations that are happening, okay? All right, so next up on our transformation, we've got this x plus pi over 4. So what does that do to our graph? Yeah, that's going to go to the left, pi over 4. Because what number can we plug in there to make it equal 0? Well, negative pi over 4. So that becomes our new center point. And the equation we write should be tangent of x plus pi over 4. So just the part of the equation that tells us to move it to the left, okay? And again, with these ones, I would move the asymptotes first. So if I'm going pi over 4, where do I move the lime green asymptote to? Like, how many boxes do I count over? 4 boxes? 2 boxes? 1 box? Yeah, we're gonna move this over 2 boxes, okay? So if I'm going to the left, that means it's gonna go here. And then I can move everything over 2 boxes. So this other asymptote goes here. Whoops, nope, just kidding. Here. And our center point moves. Nothing else changes. And so that's where we get our shifted graph, okay? Now that last part, the 1/2, right? That 1/2 is going to mean that there's a half a branch where there was 1. Okay, there's going to be a half a branch where there was 1, or we can think about that's a stretch horizontally. Okay, so we're going to take these asymptotes and we're not going to squeeze them in closer together, but we're going to stretch them out further. Okay, but the one thing that remains constant, draw in that center point. That one doesn't move, but we're going to move the asymptotes around that, okay? So before we think about that, we know that this right here is sort of the period for the branch, and that is pi. What's the period of the new branch going to be? Like, how long will it take one branch to happen? All right, Thea, you say pi over 2. Pi over 2 would mean, though, we were having something that was shorter. So we'd be like compressing it. Yeah, we actually want to go the other way, okay? So what Arlette said is correct. We're actually going to be stretching this out so that our period is now 2 pi, okay? Well, if we think about how far we need to go, we can think about counting in terms of boxes, okay? So from the center point to this asymptote is 1, 2, 3, 4 boxes. Now, if we want to make this distance twice as long, I need to count out 8 boxes before I put in my vertical asymptote. So I'm going to count out 1, 2, 3, 4, whoops. 1, 2, 3, 4, 5, 6, 7, 8. So that's one asymptote. And I have to count out 8 boxes in the other direction. So 1, 2, 3, 4, 5, 6, 7. We'll call this 8 right here. And if we sketch the branch inside, we'll see that it's much more stretched out than the branch from the previous picture, okay? Yeah, that's a great summary right there in the chat. So that might be something that you write down in addition to the notes here, that the bigger the number, the more frequent we see the branches, and the smaller the number, the less frequent we see those branches, okay? And don't forget to write in your equation here. To cap things off, okay? All right, so let me sort of zoom out for a moment. You can take a look at this all on one page. Any questions on example 2? Well, if there are no questions right now, then we're actually going to take a break right now. And when we come back, we'll finish up 6.2, and then we'll get started on 7.1, okay? So I'm going to go ahead and stop sharing this. All right, folks, welcome back. I have started the recording. No, do not fear. Okay. All right, here's what we're gonna do. We're gonna go over one of the graphs in the graphs of secant, cosecant, and cotangent, okay? I will make a video for the other two. The reasoning will be very similar, but I kind of want to do one just so we've kind of seen the process, and I think it'll help you answer some of those last quiz questions for quiz 7, okay? So we're gonna start the share for 6.2. Okay. So when we look at the graphs of secant and cosecant and cotangent, where do they come from? They actually come from their reciprocal functions, okay? And so we're going to talk through the graphs of sine and cosecant, and then I will, like I said, make a video for the graphs of secant and cotangent, okay? But I think this first part is nice to kind of talk through one time. So when we think about sine, we know based off of our graph that the domain is all real numbers, right? That's something that we learned last week. And that the range for sine is actually restricted in that the smallest values are -1 and the largest values are +1. And so that's why we use those square brackets to describe every number between -1 and 1. And then we talked about whether it was even, odd, or neither, and we learned that sine is an odd function. And just to kind of help prepare you for that even odd question on Friday's exam, one of the reasons we know it's odd is because f of -x equals -f of x, okay? And so can someone tell me the relationship between sine and cosecant? So how do we relate sine and cosecant? They're both odd, yeah. How do we get cosecant from sine, though? Maybe that's a better question. How do we get cosecant from sine? Yeah, so not only are they both odd functions, but cosecant is actually 1 over sine, right? So we could say that cosecant of an angle equals 1 over sine of that angle, right? So they're reciprocal. Exactly, they're reciprocal function, okay? And so when we look at the reciprocal functions, we know we can just sort of do 1 over that number, or we can sort of flip a fraction if that's what we have. And so that's exactly how we get the graph of cosecant. So if you go to Desmos and you graph cosecant, you're going to get something like this. And it looks like a lot of parabolas that sort of keep going, and some of them are facing up and some of them are facing down, and there's sort of these weird spaces in between them. But if we think about where it came from, we can kind of unpack, like, why does it look like that? Okay? So let's do that. Let's pick a point. Let's say we were looking at this point on the sine graph, okay? So what is the y value at that orange point? This is an easy question. What's the y value there? Yeah, it's just 1, right? So we have 1. Now tell me, what is the reciprocal of 1? It's 1. Okay. That's where that orange point came from on cosecant. Okay, we literally took the y value from the point on sine and we did 1 over that to get the point on cosecant. Okay. What about this point? The y value of that point on the sine graph is -1. What is the reciprocal of -1? -1. And check out where that point is. -1. Okay? So if we just picked some of the nicer numbers and we found the reciprocal, we would get like 1 and the negative ones. But that doesn't really describe why we have some parabola looking things that are facing up and some that are facing down, okay? So let's pick some that might be, I don't know, a little less nice. So for example, what if I zoom in here for a little bit and I find that this point right here has a y value of 1/2. What is the reciprocal of 1/2? 2. Okay, well, let's see where that point is on the cosecant graph. So if I just go straight down to find that same angle, check out what the y value is. It's 2, right? So because the reciprocal of 1/2 is 2. I bet we can find another point that has a y value of 1/2. Maybe like over here. And if we think about the reciprocal of 1/2, well, that should give us another y value of 2. Okay? So if we took every single value on the sine graph, every single y value, and we found the reciprocal, what would we get? Well, we would start to get some shapes that are sort of going up like a U and some that are kind of like an upside down U. But that doesn't explain all the gaps that we have. So this green point right here, okay? What is that y value? It's 0, okay? What is the reciprocal of 0? Okay, so what is the reciprocal of 0? 1 over 0. Okay, so now this is really important, folks, because some of us are still confusing what it means to divide by 0. If we have 1 over 0, does that give us 0 or does that give us undefined? Which one does that give us? Yeah, that gives us undefined. And so what undefined looks like, exactly, it creates a vertical asymptote every time you divide by 0. So if we compare these two graphs, every time the sine graph has a y value of 0, we're going to have a vertical asymptote in cosecant. And so where does that happen again? It happens at pi, 2 pi, negative pi, negative 2 pi. And check this out. All of those have vertical asymptote. Okay. So that's why these graphs look like that. Like the cosecant one looks so weird because we're taking reciprocals of numbers, and sometimes there's a number where when we take the reciprocal, we get an undefined, okay? So that's where all of these vertical asymptotes come from. Now, if we think about the domain and range for these, well, our domain, we could say is, instead of using interval notation, we could say it's all of the numbers, except what can x not equal? Can someone give me an example of what x cannot equal? Or rather, where are the vertical asymptotes? Okay, 0, where else? 2 pi, where else? Negative pi, so good. Okay, so we could say that x equals k. So k is kind of like the other k we said. K is a multiple of pi. So all those answers that you folks said are multiples of pi. 2 pi, negative pi, 1 pi, 0, all of those are multiples of pi. Okay, so this is a fancy way of saying multiples of pi. Right? And Christina, I loved your comment about, is that why the tangent graphs also have vertical asymptotes? And that is exactly correct. So we think about how we get tangent from sine divided by cosine. So everywhere that cosine is 0, tangent is going to have a vertical asymptote. Okay, so it does go back to that idea of just dividing by 0. That's a great observation. Okay. All right, in terms of range, and again, I'm not expecting you to be able to recreate the domain and the range for this. I just want us to see it, experience a little bit of like stretching our brains around notation, okay? But the range for this, we could say that there's sort of one group that's on the bottom all the way to 1, or sorry, negative 1, okay? So those would be all the things that are facing down. And we start again from 1 to infinity. So those would be all the branches that are facing up, okay? But we actually have nothing in between negative 1 and 1. We just have everything below negative 1 and everything above negative 1, above positive 1, okay? And then as far as even, odd, or neither, based on the picture, what do you folks think? Is this one even? Like, do we have symmetry here across the y-axis? Or is it odd? Or we have the symmetry around the origin? Which one does this look like? Okay. So I think this one's a little bit harder to see, right? It's easy to get distracted by the vertical asymptotes, but you can just pick a couple points to try and see what happens, okay? So let's do this. What is f of pi over 2? Like, what's the y value of pi over 2 on the cosecant graph? That's like where that orange point is. So that looks to be a y value of 1, right? Okay, so now we should maybe check out the y value at negative pi over 2, right? So let's go to negative pi over 2, and somebody tell me the y value of that point. Yeah, that's at negative 1. So f of negative x is equal to not this, but negative of that. That sure does make this an odd function, okay? So we sort of have it where it's like going up on one side and down on the other. That's a good visual cue for things being odd, all right? And Richard, I think that's a great way to say it as well. If sine is odd, then so is its reciprocal, okay? And you could even go back to the identities that sine is an odd function, cosecant is an odd. Which are the two trig functions that are even? Because there's only two of them. Right? Which two trig functions are even? Yeah, cosine and secant. You got it. You got it. Cosine and secant. Okay. And so we're going to stop our discussion here in terms of the graphs of secant and cosecant and tangent. All right. But I wanted us to kind of walk through this process once at least, just to say that we've done it, to get a little review of what it means to be even or odd or neither, and maybe see some of this new notation. Okay. As far as the exam 2 goes, I'm really only looking for the graph transformations of tangent. Okay, I do ask a little bit on quiz 7, like where do the graphs of cosecant come from? So I want us to kind of be able to describe the process, but you don't have to remember the picture of the graph. You don't have to remember the domain, the range, and even odd neither. Okay, so just to make sure that point is clear. All right. So this kind of brings us to the end of where we're going to talk about in class. I will make a separate video that will talk about the same process for cosine and secant, and also the process of tangent and cotangent. Okay, so if you want to geek out on that a little bit later, you are welcome to do so on your own time. Okay, so I'm going to stop sharing here. I'm actually going to stop.